Hi, everybody. This is David Wilson with Physics 150, and there was a lot of requests for more lecture in the midterm survey, and so I wanted to address that a little bit and give folks a lecture on momentum, which is a topic I think can be quite confusing. The first thing I want to say is the following. People who study educational research, that is, they study how people learn or how effective learning can be through different methods from either working in a group or listening to lectures, watching videos, etc., have found very clear evidence. And that clear evidence is the following. The least effective way to learn something is to listen to someone talk about it. And this has been shown again and again and again. When I first went to graduate school, this was told to me. I didn't really believe it at the time, but over the years, I've seen just more and more studies that have looked into this. And the least effective way, really, to learn a material is to listen to a lecture on it. So, what is the point of lecture? Lecture can, as it turns out, it can teach you something. It doesn't teach you much. Lecture normally connects ideas in our minds. That is, if you knew a bit about a subject and you went to see a lecture about it or listen to a lecture about it, you might realize, oh, topic A is connected to topic B. I get that. That makes sense. When I've surveyed students in the past in in-person teaching, and I say to them, okay, what did you learn in your last lecture course, or in the last lecture, even that same day? When I ask students, what did you learn in lecture today? Most can't tell me anything, even if they had just come from a course in which there was lecture. And sometimes they go, oh, I learned the following. And I go, that's great. You didn't know that beforehand. And when they think about it, they go, well, I guess I did know all those pieces. I just didn't realize how they connected. So lecture for new information really isn't that helpful. Um, and there's another role, however, that lecture can play. And that is, you can think about there's a barrier to learning, right? It's hard to sit down and read a book or to look at something that's brand new and to make sense of it. Lecture can lower that activation barrier. Lecture can make it a little bit easier to engage with a topic. Lecture can help you understand something you're trying to understand, but it really is a poor communicator of new information. There's another reason that we don't do a lot of lecture, because we get asked for it. Every year the students go, please give us more lecture, please give us more lecture. And we're pretty universal in our feeling on this. It's unethical for us to lecture to you. Why? Well, we're asking you to give us a whole bunch of time. You think about it, there's 90 of you in here. So everybody gives me an hour to listen to a long lecture. That's 90 hours of productive time that you've now invested. And if I know that efficiency is very low, then I think there's a problem with that. I think it's unethical for me to just dump information at you when I know you won't learn from it. And I know you won't learn from it based on not only my own observations, but based on the research in the past. Does that mean that all of your lectures are worthless or all of your lecture courses should be changed? Probably not. I'm not going to speak for another discipline. I'm going to speak to physics. And within physics, we know that watching us do things is a poor communicator. And so I would challenge you to think about future lecture courses and how useful you find them to be. In physics, we know unequivocally it is not a great way to communicate information. However, it does communicate some things, and so I'm going to move or try to use that. And I'm going to talk to you today about momentum, which is a topic, if you have taken physics in high school, you may not have seen or may not have seen very well. If you've never taken physics, you may not have heard of momentum, other than maybe in like sports analogies or something like that, or politics. So let's talk about what is momentum from a physics point of view. So there's the simplest definition I can give you is it's a vector quantity that when carefully accounted for is found to be conserved. So first off, what's vector quantity? Vector quantity means that momentum has not only a direction, but an amount. So if you think about velocity, velocity is a vector quantity that you know about. Velocity is, say, 50 miles per hour north, or 50 miles per hour in the x direction, or 20 kilometers per second in the y direction. So it has an amount and a direction. And then I say, when carefully accounted for. What do I mean by carefully accounted for? Meaning that if you consider all of the ways that momentum could have changed, you find it is conserved. Conserved, what does that mean? In physics, this is a very special term. Conserved means that something does not change from beginning to end. So no matter what's happened in the interim, the amount you had at the beginning is the amount you had at the end. So in this case, because momentum is a vector quantity, the amount you have in the beginning and the direction it is directed, so if you have momentum like this, then a whole bunch of things happen, you're still going to have momentum like this at the end. So let's talk about notation. Again, momentum here is going to be given by the symbol of P. Why? I don't really have a good answer for you. There's not a lot of P's in the word momentum. This probably comes from impetus. Isaac Newton gave it the letter P. We're not really certain, but we've used it ever since. So when we talk about momentum, we might talk about momentum of object 1 or object 2, which we denote as P1, P2. And sometimes you'll see us write PI, where I is a variable meaning 1, 2, or whatever. So momentum can be found by multiplying the mass of an object times its velocity. And that's velocity is where the vector comes from. So P1 would be M1, B1. P of a system, if that's a two-body system, would be P1 plus P2. Again, each of these are vectors. So here's something interesting about momentum. If it's conserved, that means the amount you have at the beginning has to be the amount you have at the end. So we're going to see that when you have two objects, any momentum lost by object 1 is then gained by object 2. Again, this is what we mean by conserved. Mathematically, what do I mean by change of momentum? Well, change in physics is, again, one of these things that has a very specific definition. It's always final minus initial. So delta P1, or how did the momentum, the vector quantity of object 1 change? It changed such as you take the final, subtracting the initial. Now, I just said any momentum lost by object 1 is gained by object 2. So this mathematically means the following, that the change of P1 is equal to the negative change of P2. And we're going to see why in a moment. So students will often write this down algebraically. They'll use it. You never start here. We'll see why in a minute. But you never start here. But I wanted to point this out because this minus sign is such a common error, meaning that students will write it down here, and they might even write it down here, but then they forget to distribute it inside of that parentheses. So you have to be very, very careful with your signs and momentum problems. One mistake can prove fatal to the whole problem. Now, change of momentum, or how momentum is added or taken from a system, is a very special thing in understanding physics as well. So special that we've said the change of momentum is actually known as impulse. Well, so what does that mean? So impulse we often think of as momentum added to something. So impulse could be a baseball bat against a baseball, right? If you were thinking about the baseball as your system, the bat striking it would impart an impulse on the ball, which would not only change how fast the ball was going, but which way the ball was going. So we often will, refer to something as an impulse occurring, especially when we think about it being added from outside. But it doesn't have to be from outside, it can be inside too. So J1 would be the impulse on mass 1, and J2 would be the impulse on mass 2. So you've got two new symbols in this chapter, J and P, and you're going to see them a lot, and you're going to have to understand what they mean. So one way to think about impulse is that it's a transformation of momentum from outside the system or within the system from one object to another object. All right. So why do we look at momentum? We already have kinematics, right? We have these equations that when the acceleration is constant, we can tell you how high an object's going to go, how fast it's going to go, where it's going to land, how high or how long it's going to be in the air. Kinematics is really powerful. And sometimes we don't know what our accelerations are. So we find them from masses or from forces. That's what we did last chapter. So if I can tell you all this predictive power, where something's going, how long it's going to take, why momentum? Well, as it turns out, through careful observation and measurements, we found that it's conserved in physics or conserved in nature, conserved in the universe, right? And so again, conserved is this very special thing. Conserved doesn't mean there are no changes. What it means is that the sum of all those changes will yield the same value. So another way to think about it is total momentum is not created or destroyed. You can create momentum of an object or create momentum of another object from some kind of interaction, an explosion or something like that, right? If you have something blow up, there was no momentum before it blew up and a lot of momentum after. But as it turns out, the amount of momentum each object gets when you add it all up adds up back to zero. We're going to see how that works in a minute. So conserved is a weird term. It means that the net amount, the total, when you add everything up carefully, doesn't change. All right. So now let's look at how does momentum change in time. So If you think about change, anytime you think change, think like either a finite amount, delta, or in a more nuanced way, calculus, a derivative. So if we calculate the derivative of them with respect to time, that means take d dt of mass times velocity. And again, this is the momentum of an object, object 1. Well, this derivative has to do what we call the product rule, right? So in calculus, we take the derivative of mass times my velocity, add it to mass times the derivative of velocity with respect to time. That looks ugly, right? And unless you know math and you're not scared of it. But for many of us, we look at it and go, what the heck is going on there? Well, let's look at it in a very specific case to understand it. In a special case in which dm dt, sometimes you might see it written as m dot. This little dot on top means a time derivative. If you're a physics major, you should really remember that. So it means that m dot is 0. What does that mean? Well, it says the change in mass, the instantaneous change of mass with respect to time, is 0. Let's think about that for a second. What does it mean that the change in mass is 0? It means you're not losing any mass, right? So if you have two balls bounce off each other or something and you didn't lose any mass anywhere, dm dt is 0. So if we take that term and we eliminate it, then what we have is dp dt is ma. We know what that is, right? ma is the sum of the forces on object 1. So if you remember Newton's second law, we were told that if you add up all the forces, right, add everything up, that you can set that equal to ma. And we didn't know why that was true. We just knew that it was. Well, where does that come from? That comes from the understanding that the total momentum of a system will not change. And for that to not change, it means the sum of all those forces has to be ma. If you're a physics major, you'll see more of this in Physics 340. For the rest of you, I just want you to kind of carry that notion in your mind that because momentum is a conserved quantity in nature, that means that Newton's laws are true. And so all 3 Newton's laws come out of this understanding of momentum. All right. Well, what about multiple objects? What if you're not just like one object? What if I've got several? So let's imagine this is my setup. And in this setup, I've got object 1 with momentum coming this way, and object 2 with velocity this way, so it's got some momentum going in that direction. And I just realized I inadvertently wrote velocity here, and I did not mean to. I meant to write momentum. So this is momentum of object 1 initial, and this is the momentum of object 2 initial. So how is that different from velocity? Remember that P2I is mass V2I. So I'm not drawing velocity, I am intending to draw momentum. So let's imagine this is my setup. As one object moving this way and another object is moving that way, and they collide. And after they collide, they bounce off in the following ways. So again, here I'd need to have momentums and not velocities. So now we can ask ourselves questions. Is the momentum conserved? Well, as it turns out, you have to be really careful about what you mean by that. Is the momentum of what conserved? So let's pause for a minute and write out our answers. Is the momentum of object 1 conserved? Is the momentum of object 2 conserved? Is the momentum of the two of them summed together is conserved? One of the reasons that lectures are not very helpful is because they're totally passive. You're sitting there, you're not thinking or anything. One way we can help combat that a little bit is we can ask you to stop and engage and to come out of audience mode, right? You might love a movie, you might remember the details of the movie, but you don't necessarily learn anything from a movie. So stop for a minute, write down your answer, think about what you've got going on, and make a guess. It turns out one of the ways we learn really well is when we're wrong. So if you make a guess and you're wrong, great. That's your new opportunity to learn. So I really want you to think about this for a minute. Pause the video. Is P1 conserved? Is P2 conserved? Is P1 plus P2 conserved? And think about that. All right. So let's look at this a little bit more carefully. Right? So we had, P1 initially going this way, and it bounces off going that way. If we just look at these two vectors, what do we see? Well, initially it was going this way, and then after the collision, its momentum is going that way. Is that the same? right? Is this vector the same as that vector? No. So was P1 conserved? No. Well, what is the change in P1, or what is the impulse that was on object 1? Well, one way to think about that is, what vector do I add to this one to make it become this one? That vector that I add is delta P1, or known as impulse on 1. All right, what about object 2? Object 2 was initially traveling to the left, had the collision, and now is traveling to the right. Is its momentum conserved? Well, we look at it. Does its initial vector equal its final vector? Nope. So is P2 conserved? Of course not. So then we can say, well, what vector do I have to add to this one to make it this one? Well, here we go. So that is delta P2 or J2. So we have a little bit of a conundrum. We talked about momentum being conserved. However, the first two objects we looked at, their momenta are not conserved. Their momenta changed. So what does that mean? Well, if I look carefully now, if I look carefully now at the system, or that is, I look at how did the total momentum in the beginning compare to the total momentum at the end, what do we see, right? What do we see? So this was P1 initial, heading down to the right. This is P2 initial, heading to the left, right? That is this vector here and this vector here, both of my initial vectors. So if I add my two initial vectors together, I see that the system's momentum is down and to the right. And then after they collide, right, what's happening? One's going this way and one's going that way. So if I add those vectors carefully together, right, I get something like this. So the momentum of the system, which is this blue vector, didn't change. The system momentum was conserved. So that was a lot. Let's back up and look at it again. And that is, if I add this vector and that vector together, right, that gave me something down to the right. If I add this vector and that vector, right, so this vector and that vector, I get something down and to the right. So that says the total momentum didn't change. And how do we understand that to be true? Well, if you look here, the change that object 1 experienced was to the left by this much. The change that object 2 experienced was to the right for that much. So if I add this vector and that vector together, I get 0. So the change momentum of object 1 plus the change momentum of object 2 equaled 0 at the end. And so that's just as simple as saying delta momentum of the system equals delta momentum of 1 plus delta momentum of 2 equals 0, or delta P1 equals negative delta P2. So there's a lot of new terms, a lot of arrows, a lot of vectors, and if you're feeling nervous about vectors, you know what you have to do right now. You have to figure them out. You are responsible for learning how they work, because we're going to use them a whole lot this coming week. We're going to use them a whole lot in the following week. Vectors will be a part of almost every problem you do for Physics 150 and Physics 152. So do yourself a favor and make sure you learn how they work now. All right, so let's look at another case. Let's think about the momentum of an isolated system. Well, momentum of an isolated system is conserved. What do I mean isolated? I mean away from other influences. There's nothing coming in and hitting it. So then how does like a rocket work? Right, so imagine you've got a rocket sitting in outer space at rest. And this rocket's sitting there, right, not moving. So since momentum is mass times velocity, there's no momentum. And then all of a sudden it starts its little rocket engine up, flames go out the back, and it begins moving. That seems, at least initially, like a violation of the notion that momentum of an isolated system is conserved, because there was none to begin with, and now there's some. Let's look at a simplified version and think about this more carefully. What does it mean that there's exhaust in a rocket? It means that some amount of mass is ejected out the back, right? The rocket's losing mass, right? The rocket fuel or whatever is now being ejected out the back. So let's look at that. That says that momentum of the system is going to equal to the momentum of the rocket plus the momentum of the exhaust. And we know if it's an isolated system, that change is going to have to be zero. So what are the implications of that? Well, the change has to be zero, which means that the change of the rocket plus the change of the exhaust has to add up to zero. That means that whatever the rocket gains is going to be negative what the exhaust gains. Or that the delta P rocket plus delta P exhaust add to zero, right? The same thing we just saw a moment ago. So the reason the rocket begins moving forward is because the fuel begins moving backwards. And that might seem weird to still think of momentum as being conserved, but remember, it's a vector quantity. So you can have two things, or you can have one thing not moving, and all of a sudden it is moving, and that's okay as long as the mass times velocity going in each direction add up to zero. And that's why we mean a vector quantity, right? This doesn't work if you just think of numbers. You have to have these signs that come from vectors. So that means the exhaust is gaining an opposite momentum as the rocket, so the total momentum of the rocket remains zero. All right. So how do we solve momentum problems? As it turns out, all momentum problems, sorry, there's some knocking at my door from my kids who promised to be quiet and not interrupt me, but they are. To solve momentum problems, we do a very similar thing as we've always done. We draw a picture, before and after. We choose an appropriate coordinate system, x, y, whatever. Then you add up all the momentum in each direction, very similar to how you added up the forces in each direction. Sometimes that means you have to break your momentum vector into components. Then we determine things like impulse, change momentum, momentum initial, momentum final, any missing quantities in terms of what's given above. But fundamentally, nothing really has changed. We're doing the same thing we did before. We're just working with a different tool. And that momentum tool, as you will see, is very powerful. Turns out you don't have to know accelerations. Turns out you don't have to know forces. All you need to understand the system is momentum. And it simplifies things quite a bit. So I hope this has been a helpful understanding of why we don't lecture in general, and a good introduction to momentum. And some of you might think, well, gosh, that really helped. Great. I'm glad that it did. But I will challenge you to say there's no new math that you can do watching it, but I am glad it was helpful. Thank you.